So in the previous lesson, we looked at how to use nodal analysis to solve circuits involving current sources. Now in this lesson, we are going to consider circuits involving voltage sources. Now with the inclusion of voltage sources, the procedure we used in the first lesson is going to be slightly different. Now the reason being that we need to consider two extra cases aside from the steps that we used in the previous lesson. Now in the previous lesson, we said that given a problem and then being asked to use nodal analysis to find the node voltages, the first thing you are going to do is to identify the reference node. Secondly, you apply KCL at the non-reference nodes to obtain the current equations, and then apply Ohm's law in order to obtain the node voltages and then solve them simultaneously. Now, in the case where voltage sources are included in the circuit, the two extra cases you need to consider is: one, if there exists a voltage source between the reference node and any of the non-reference nodes, then we simply set the voltage at the non-reference node equal to the voltage of the voltage source. So an example, let's say we have this to be the reference node, and we assume that we have a node here which is a non-reference node, and there exists a voltage source in between these two nodes, let's say 10 volts. Then we say that the voltage at this node is simply 10 volts. So if there exists a voltage source in between the reference node and any of the non-reference nodes, then we simply set the voltage of the non-reference node just to be equal to the voltage of this voltage source. That is the first case. Now the second case is if there exists a voltage source, whether dependent or independent, in between two non-reference nodes, then the two non-reference nodes form what we call a generalized node or a supernode. So the two non-reference nodes form a generalized node or a supernode. Now a supernode is formed by enclosing a voltage source which is formed between two non-reference nodes, whether dependent or independent, and any element which is connected in parallel with it. So using this idea, we are going to solve our first question and then move on to solve the next question. So in this question, we are asked to find the node voltages in the circuits below. Now you need to identify that we have this to be our first node. We have 2 amperes, 2 ohms, 10 ohms, and then 2 volts connected here. So this is our first node. We have our second node to be this, where we have 2 volts, 10 ohms, 4 ohms, and then 7 amperes also connected here. And then we have 4 elements connected at this node. Now because this is the ground, we consider this to be the reference node, and then these two to be the non-reference nodes. So first of all, you need to check if there is a voltage source in between the reference node and any of the non-reference node. Now here you realize that we don't have anything like that here. And then secondly, you check if there is a supernode, that is, there is a voltage source between the two non-reference nodes, and that is yes. And we also have an element which is 10 ohms connected in parallel with this voltage source. Now this is in parallel with this voltage source, that is 2 volts, simply because the two elements are connected at the same two nodes. That is, they are connected here and then they are also connected here. So once the two elements are connected at the same two nodes, it means that they are connected in parallel. So we are going to redraw the circuits excluding this 10 ohms. So let's redraw the circuit. So we are going to have something like this. We have 2 amperes, we have V1, 2 ohms, (2 volts), V2, 4 ohms, And then lastly, we have the current source, that is 7 amperes. So here we are going to find the node voltages, that is V1 and V2. We are going to find V1 and V2. So like we did in the previous lesson, this time we are going to apply KCL at the supernode, at this entire node. So we consider this whole thing as one single node. And so applying KCL at this node, so we apply KCL at the supernode. So applying KCL at the supernode, we have this current moving towards the node. We have current leaving the node. So we know current is supposed to move from a higher potential to a lower potential, and you know the reference node has a zero potential, so current is going to move this way. We also have current leaving this way. So this current is called I 2 ohms, and this is called I 4 ohms. And then we have current also leaving the node, 7 amperes current leaving the node. So the difference is this time we consider this whole thing to be a single node because we have a voltage source in between the two non-reference nodes. So let's proceed. So applying KCL, we have current entering, current leaving, and then current leaving. So the sum of current entering 2 is equal to sum of current leaving, I 2 ohms plus I 4 ohms plus 7. So we transpose 7 to the left hand side. We have 2 minus 7, which is negative 5, equals I 2 ohms plus I 4 ohms. Now we are going to apply Ohm's law here in order to obtain the node voltages. So let's say we have negative 5 equals, now for I 2 ohms, that is V1 minus 0 over 2 plus, for I 4 ohms we have V2 minus 0 over 4. Now let's simplify this equation. So we multiply each term of this equation by 4. So 4 times negative 5, that is negative 20, equals 2 goes here once, 2 goes here 2 times. Now 2 times V1 is 2V1 plus 4 cancels out 4. We are left with V2. So we have negative 20 equals 2V1 plus V2. Now let's call this equation 1. Now, still from this same circuit, we are going to use KVL considering this loop. So we are going to take the clockwise direction. We are going to take the clockwise direction. So always remember that you have plus minus here, especially when going around the loop. So we are going to take the clockwise direction. Now we have 2 here, so we assume current is supposed to leave the positive terminal of the voltage source. So current leaves the positive terminal, so we have plus 2, and here this is opposing the flow of the direction that we are taking, so it becomes negative V2. So we go this way, and then here it is in line with the direction because the current will leave the positive terminal, so it is in line with the direction, so that becomes plus V1 equals 0. So the sum of voltages around the loop should be equal to 0 according to KVL. Now from this we can make V1 the subject, so we have V1 to be equal to, we transpose negative V2, that becomes V2, we transpose 2, then that becomes negative 2. So we have V1 to be equal to V2 minus 2. Now let's call this equation 2. Now we are going to put equation 2 into equation 1. So from equation 1, we have negative 20 equals 2 times V1. Now in place of V1, we have V2 minus 2 plus V2. So we have negative 20 equals 2V2 minus 4 plus V2. We transpose negative 4 to the left hand side, and then we have negative 20 plus 4 equals 2V2 plus V2, that is 3V2. So this becomes negative 16, and that is equal to 3V2. Now we divide through by 3, and then we have V2 to be equal to negative 5.33 volts. So this is the value of V2. Now let's put V2 into equation 2. So from equation 2, we have V1 to be equal to V2, which is negative 5.33 minus 2, and that is equal to negative 7.33 volts. So therefore, we have V1 to be equal to negative 7.33, and then we have V2 to be equal to negative 5.33 volts. So now let's move on as we solve the next example. So with example 2, we are going to find the value of I and then V in the circuits below. Now, as usual, first of all, we need to check if there is a voltage source in between the reference node and any of the non-reference nodes. You realize that there is a voltage 21 volts between the reference node and this non-reference node. And so we simply set the voltage at the non-reference node to be equal to the voltage of this voltage source. So we have this to be 21 volts. Now, even before that, you should realize that we have 4 nodes in here. So we have this voltage source, and then this 4 ohms resistor connected at this node. We have 4 ohms, 3 ohms, and then 9 volts also connected at this node. And then we have 9 volts, 2 ohms, and then 6 ohms also connected at this node, which is the third node, and then the 4 elements connected at this node. So we have 4 nodes in here, and we call this the reference node. So these 3 are non-reference nodes. Again, you realize that we have a voltage source in between the two or these two non-reference nodes, which means that we have a supernode here. So we have a supernode here. And mind you, this time there is no element connected in parallel with this 9 volt source. So that is exactly the circuit we are going to deal with. Now let's assign current in the circuit. So we have current I 4 ohms entering the supernode. We have current I 3 ohms leaving. We have current I also leaving, and then we have current I 6 ohms also leaving. So we are going to apply KCL at the supernode. So we have current I 4 ohms entering. So I 4 ohms will be equal to current leaving I 3 ohms plus I 6 ohms. So sum of current entering is equal to sum of current leaving. Now we have I 4 ohms to be 21 minus V1. So this is V1 and this is V2. So we have 21 minus V1 over 4 equals V1 minus 0 over 3 plus V2 minus 0 over 2 plus V2. Notice that these two elements are connected at the same node. So we still have V2 minus 0 over 6. So we multiply each of the terms here by 12. So 4 goes here once, 4 goes here 3 times. So we have 3 times 21, which is 63, minus 3 times V1, that is 3 V1 equals 3 goes here once, 3 goes here 4 times. So 4 times V1 is 4 V1 plus 2 goes here once, 2 goes here 6 times. We have 6 times V2, and then plus 6 goes here once, and then here 2 times, so plus 2 V2. Now let's simplify this equation. So we have 63 on the left hand side equals, we transpose negative 3V1 to the right hand side. So 3 plus 4 becomes 7, 7V1 plus 6V2 plus 2V2, we have 8V2. Let's call this equation 1. Now the next thing we are going to do is to apply KVL to this loop. We apply KVL to this loop. So this time we are going to move also in the clockwise direction. So we have 9 volts. So KVL says the sum of voltages around the loop should be equal to 0. So we have 9 volts moving in the clockwise direction. It is opposing the flow of the direction we took, that is the clockwise direction. So this becomes negative V2. And then we are still in the clockwise direction. This is in line with the direction, so this becomes positive V1. So plus V1 equals 0. Now let's make V2 the subject. So we have 9 plus V1 equals V2. We call this equation 2. Now the next thing we are going to do is to put equation 2 into equation 1. So for equation 1 we have 63 equals 7V1 plus 8 times V2, which is 9 plus V1. So we expand the equation, and then we have 63 equals 7V1 plus 8 times 9 is 72 plus 8 times V1 is 8V1. So we add 7 and then 8, and then we have 15. So this becomes 63 minus 72 equals 15V1. 63 minus 72 is negative 9, and then equals 15V1. We divide through by 15, and then we have V1 to be equal to, now 3 goes here 3 times, and then 3 goes here 5 times. So we have negative 3 over 5, which is equal to negative 0.6 volts. Now notice that V1 is the voltage at this non-reference node, and it is the same as the voltage across this 3 ohms. Hence, we say that V1 is equal to V, and that is equal to negative 0.6 volts. Now let's move on as we find the value of the current I. So even before that, let's try to find V2. So from equation 2, we have V2 to be equal to V1 plus 9, and that is equal to negative 0.6 plus 9. So we have V2 to be equal to 8.4 volts, that is V2. And then we know that I happens to be the current flowing through the 2 ohms resistor, and then the voltage at this node is V2. So therefore we have I to be equal to V2 minus 0 divided by 2. So it is 8.4 minus 0 over 2, and then 2 goes here once, 2 goes here 4 times, 2 goes here 2 times. Therefore we have I to be equal to 4.2 amperes. So that's it for this video. Thanks for watching and see you in my next video. Bye bye.